Okay, so here we're going to talk about how carbohydrates are digested. And overall, we're going to discuss dietary fiber. We're going to discuss how glucose, galactose, and fructose are going to be absorbed, and then how they're absorbed from the gut and then by individual tissues as well. But first, we have to start with digestion. And so some terminology I'd like to introduce before we get into how these carbohydrates are digested are listed here. We have our enzymes, our glycosidases, that are going to hydrolyze our glycosides, which are basically our carbs. And so we have glycoside, a sugar bound to another functional group by a glycosidic bond, and that's going to be the target of our glycosidase. And we've already talked about glycosidic bonds. We have the alpha-1,4, we have the alpha-1,6, the beta-1,4, beta-1,6. And so we have glycosidases that are going to be able to target different glycosidic bonds. And then we also have something called a dextrin. A dextrin is going to be substances that have been polymerized by glycosidic bonds, and they are made up of alpha glucose molecules. And so dextrins are basically our starches, our polymers of glucose with the glycosidic bonds that our enzymes can break down. Now we have amylose, which is what is your dextrin is going to be broken down into, and amylose forms a straight chain. And so these are straight chains of glucose. And we have amylopectin, which is going to form a branch chain of glucose. And again, it's going to be a product that forms as we break down our polysaccharides, our starches. And a limit dextrin is going to be short branch chains that are remnants of the amylopectin as it's being broken down. So in general, just very overview sweeping, we're going to start with a polysaccharide. That's going to be our starch. We have an enzyme, the alpha-amylases, that can start to work on these very large molecules. They're going to eventually become disaccharides. And our disaccharides are going to be sucrose, maltose, lactose. And then these are going to have enzymes that can break them down into our monosaccharides, our glucose, fructose, and galactose. All of these can be absorbed, and then they can be stored as glycogen. So glycogen is, again, a polysaccharide. So you start with a polysaccharide, and your body can make a polysaccharide. Okay, so basically we have our glycosidases, we have our alpha-amylases that are going to start and get everything going. We have saliva and pancreatic versions that we'll talk about. Your alpha-amylases cannot work in the stomach, and so that's why you have two of them. The saliva will start to break it down, and then after your starch passes through your stomach, your pancreas will release another alpha-amylase to continue breaking down your starches. Your disaccharidases are going to be on the intestine brush border, and then we have a few glycosidases we have to talk about. We're going to have a glucoamylase, which hydrolyzes alpha-1,4s of our dextrins. And then we have a sucrase isomaltase complex, and this is going to be important because it's going to be the complex that will hydrolyze the alpha-1,6 bonds as well as 1,4 bonds. We have a lactase glycosylceramidase, beta, which is also referred to as a beta-glycosidase complex, and this is going to help with our lactase and our glycolipids. So when sugars are attached to ceramide, for example, this is the enzyme that will release ceramide and glucose so you can absorb the glucose. And again, you're going to take in your sugars in the form of a starch, a polysaccharide, or lactose or sucrose. You're going to start digesting with alpha-amylase. You're then going to get it neutralized in the stomach. The pancreas will release its own version of alpha-amylase and bicarbonate to neutralize the stomach acid. And then you're going to get tri and oligosaccharides. In the small intestine at the brush border, you're going to have your disaccharides broken down into monosaccharides, and the monosaccharides are what get absorbed. So carbohydrates are going to be about 40% of our total calorie intake, so it is a large part of our diets. And we're going to have some carbohydrates that are not digestible, such as cellulose. And so this is a fiber that is not digested. And so it's simply because we do not have the enzyme to digest your cellulose. And we also are going to have the lactose and sucrose, which are disaccharides, and these are going to have different glycosidic linkages. So in lactose, we have a beta-1,4. In cellulose, we have a beta-1,4. So this beta-1,4 in cellulose is between glucose and glucose. The beta-1,4 in lactose is between galactose and glucose. So we have lactase that can recognize the beta-1,4 between galactose and glucose. We do not have an enzyme that can recognize the beta-1,4 between two glucose molecules. Now there's also an alpha-1,2 link between our sucrose between fructose and glucose, and again we do have sucrase that can recognize that alpha-1,2 link. Now with respect to our dextrin, as it gets broken down, it's going to get broken down into amylose and amylopectin. And the difference between amylose and amylopectin is that amylose pectin has branches. So it has those alpha-1,6 branches. And so your amylose is going to be a large molecule, there's an N, and it's going to be a chain of glucose. And your amylopectin is going to be a chain of glucose with branches. But we have enzymes that can deal with that. The alpha-1,6 glycosidic linkages and the alpha-1,4. And so you can have starches that are hundreds to millions of glycosyl units, these glucose units, and they can all be broken down. Now with respect to salivary and pancreatic alpha-amylase, again, we're going to digest the starch, and it's going to become amylopectin and amylose. You're going to have branches or straight chains. And this is going to begin in alpha-amylase in the saliva. And then this alpha-amylase is only going to be able to hydrolyze internal alpha-1,4 bonds. And this is why it is called a endoglucosidase. Endo means in between. And so it can only work on bonds that are in between. Now your salivary alpha-amylase gets inhibited by carbonate again from your pancreas, in addition to secretion of the pancreatic alpha-amylase will continue the digestion. Has the exact same sites that it's going to bind to and hydrolyze those internal alpha-1,4 bonds. It's important to note that your alpha-amylase has no activity towards the alpha-1,6 bonds. So here's a diagram that shows the activity of your alpha-amylases. So again, it's attacking the alpha-1,4 bonds that are internal. So it's not working on the ends. It's going to break these starch into smaller pieces, random sizes, some with branches, some without branches, and you're going to get different sizes. You're going to get isomaltose, maltose, you're going to get alpha-dextrins, again, having branches. You can get some trisaccharides, oligosaccharides, which are larger, and so it's all going to be very random. Now your alpha-amylase is going to, again, not be able to work on alpha-1,6 bonds. And then your alpha-amylase is also not going to be able to work on the non-reducing ends of a chain. So remember, in your glucose, you're going to have your anomeric carbon, So you have carbon 1, this is your reducing end. And then carbon 4, this is your non-reducing. And this is glucose. And so your salivary and pancreatic alpha amylases can attack the reducing end and those alpha 1,4 bonds internally, but not any non-reducing ends. And so you're going to have other disaccharases are going to come up and finish the job.